Welcome, friends. We are now at the third module of this course, Network Theory. This is third module is all about three-phase AC circuit. Now, previously we have discussed in the previous module, that is single-phase AC network, where initially we have studied that if a coil is placed in a magnetic field is acting in this direction, and if the plane of the coil is placed perpendicular to the magnetic field, direction of the magnetic field, then flux cut is zero, hence EMF induced is zero. Now if it is rotated by some angle, then flux is cut and hence EMF is induced, and from 0 degree, when the rotation is taking place, then a flux is increased, flux induced in the coil increased, and as a result EMF is induced. And when it is placed at this 90 degree, that means the plane of the coil or plane of the conductor is the parallel to the field lines. At this position the flux cut is maximum. So at this position flux cut is maximum, hence then EMF induced in the coil is maximum. Again another 90 degree rotation in this way, so from maximum value again EMF starts decreasing, and when it again placed 90 degree, the plane of the coil is 90 degree to, when the plane of the coil is placed 90 degree to the field lines, again flux cut is minimum or zero rather, hence EMF induced zero. So this is the half cycle, and this repeats again for another half cycle. So from 0 to it increases to the negative maxima, and again from negative maxima it comes to 0. So in this way the single phase EMF is generated. We have understood this fact in the previous module. Now in this course, or in this module rather, it is three-phase AC source. Now three-phase AC source can be generated in the same manner. Instead of providing one coil, we provide three coils placed 120 degree to each other, as shown in this diagram. So if you consider this diagram, so this is north pole and this is south pole, and we have three conductors. We have three conductors, like first conductor is R1 R2, first conductor is R1 R2, this is R1 and this is R2. Second conductor is Y1 Y2, second conductor it is Y1 Y2, and third conductor is B1 B2, B1 B2. So these three conductors B1 B2, these three conductors B1 B2, then we have Y1 Y2, Y1 Y2, and last we have R1 R2, we have R1 R2. Now these conductors are placed. Now the position of placing is that 120 degree apart. They are placed 120 degree apart. So when just following the same logic that we have understood in case of a single phase AC supply, so if these three conductors are rotated with an angular speed omega, then this sort of waveform is generated. This sort of waveform is generated. So this waveform is the R phase, that is the one of the phases, right? The second waveform is like this. This is the second waveform by yellow. And the third waveform is given by this blue waveform, and they all sinusoidal in nature. However, they are separated each other by 120 degree in phase displacement. So if you consider VR, so VR is, it's a reference phasor, it is VR sin omega t, which is written here, and applying the phasor conception or phasor notation, it is written V, its magnitude is V, but angle is 0 degree. The second one is the, this is blue phasor or yellow phasor, sorry, it is Vy, so it is lagging than the R phase by 120 degree. Lagging than the R phase is 120 degree. So Vy is lagging than R phase by an angle of 120 degree. And lastly, the third phase is 240 degree lagging, that is the B phase. So RYB normally stands for red, yellow, blue. So VB is this, stands for uh, 240 degree lagging than the reference voltage, that is R phase voltage. Now if you can see that it is a balanced system, it is a balanced system, it is a balanced system where for a balanced system the phasor summation, if this is VR or phasor representation, this is VR, then V next phase is Y, so this must be Vy, it is lagging by an angle of 120 degree. Lagging of 120, lagging means it stays behind than R, so it is a, it is clockwise rotation, that is in the negative rotation. And for the third phase VB, for the third phase it is again lagging by 120 degree of that Vy, so VB is something is directed along this direction, so again this is another 120 degree. So this is a phasor representation of a balanced system. This 120, for a balanced system, this 120 degree phase displacement between any two phases is very important. If this phase displacement is not at 120 degree, then that system is called unbalanced system. So a balanced system, two important aspects. First of all, this phase displacement between phase displacement, sorry, any two phasor phase displacement between is any two phasor is 120 degree. This is number one. And number 2 point is each phase magnitude is same. That means every phase magnitude is Vm. So that is a characteristics of a balanced system. That is a characteristics of a balanced system. So from the idea of the single phase alternating quantity generation, we have understood that if three conductors R1, R2, Y1, Y2, B1, B2 are placed 120 degree apart from each other, then similar sort of waveforms can be generated with three phases. Each phase is separated by other by an angle of 120 degree, provided each having the peak value of Vm. So this value, peak value is, this value is Vm, that is the peak value of the alternating voltage. Now what is the, why at all we require three phase system? That is the first question. Why at all we require three phase system over single phase system? In order to understand this fact, we can have some calculations. Let us say for three phase system, we have Vr is equal to Vm sin omega t, which can be written as Vm angle 0. Similarly, next phase y, Vy is equal to Vm sin omega t minus 120 degree. So it is written as Vm minus 120 degree. Vb, then it is equal to Vm sin omega t minus 240 degree, that is, so they are the phasor representation. Now if you expand this in the cosine and sine term, cos 0 plus j sine 0. Similarly, if you expand this, it will be cos 120 minus j sine 120, and similarly for B phase it is Vm cos 240 minus j sine 240. So now if you add all these three, if you add Vr plus Vy plus Vb, so if you add all these three, then if you add Vm cos 0, so you will get 0. And that is a very important result. So summation of all phase voltages, or rather I can say that summation of all voltages in each phase is 0. In the same way, we can write for current equation as IR plus IY plus IB. That is also 0. That is also true, because current equations can also be represented in same fashion. Now let us say we have three resistances. So let us say we have three resistances. resistance 1 R1, then we have resistance 2, then we have resistance 3 R3. Now we are giving supply to each resistance by 3 individual sources like this. This is V1. Again we are supplying resistance 2 as V2 from the source V2, and we are giving the supply to the R3 from the supply V3. So how many conductors are required to make this circuit? So this is the conductor number 1, this, and again one return conductor, conductor number 2. So for the second circuit we have conductor number 3, then conductor number 4, and similarly for the third one conductor number 5 and conductor number 6. So altogether we require 6 conductors to give supply. Now these 3 resistances R1, R2 and R3, you can think them as a load. You can think them as a load. So in order to supply 3 loads, in order to give supply to the 3 loads, from 3 individual sources 6 conductors are required. That is very important. From it quite obvious. Okay, from 3 loads, if you have the 3 loads and if you have the 3 separate single phase sources, you require 6 conductors. Now suppose if the 3 conductors are arranged like this, if 3 conductors are arranged like this, that means suppose each conductor, that is if this is that, if let us say this is R1, let us say R2, let us say R3, same 3 resistances. So if this is supply 1, V1 is given to, now suppose not V1, rather we are giving 3-phase supply. We are giving 3-phase supply. Now we are giving 3-phase supply. What is 3-phase supply? 3-phase supply is this. 3-phase supply is this: Vm sin omega t in R phase, Vm sin omega t minus 120 degree in Y phase, and Vm sin omega t minus 240 degree in B phase. 3 phase. So this is maybe R phase, this is maybe Y phase, and this is maybe B phase. So we are giving the same 3 resistances R1, R2, R3 by a 3-phase supply. Now instead of using 3 single phase separate supplies, we are giving supply from same 3-phase source. So this is R phase is going to R1, Y phase is going to R3, and B phase is going to R2 maybe. So suppose one current is flowing, this is, let us say I1, let us say this will be I2, let us say this should be I3. So now you require, so currents are flowing through the resistance, but so you need to a return conductor. You need a return conductor to get or to give or to provide the return path. To provide the return path to the ground or maybe supply neutral. Okay. You get a return path. So through this path, through this neutral path that is connected, or through this return path, the current should be I1 plus I2 plus I3. However, we have previously shown that the summation of all three currents are 0. So if this I1 plus I2 plus I3 is 0, so effectively what we can see here is that this conductor, this return conductor is not required at all. It is not required at all, because return current, which is I1 plus I2 plus I3, which should return through this path, is actually 0. So if there is no current, then we don't require this path. So instead of applying three different loads from three different single phase supply, so if you adopt, or if we adopt a three phase supply, if you adopt three phase supply, we can use, or we can send, or we can deliver the same amount of power only by using three conductors, only by using three conductors. So that is the biggest advantage of the three phase supply system over single phase supply system. So this is the characteristics of balanced system. However, the system is not always balanced. So if system is not always balanced, for unbalanced system, this summation is not equal to 0. I1 plus I2 plus I3, it's not equal to 0. So some current will be flowing, and that current is said IN, which is called neutral current. So to provide the path for the neutral current to flow, we require another conductor. So either for a balanced system we require three conductors, or for unbalanced system we require four conductors. So in this way we can understand that instead of using three single phase AC supply, if we use one three phase supply, it will be much better condition in terms of conductors material saving. In one case we require 6 conductor material, in another case we may be requiring either 3 conductors or 4 conductors. Now the immediate question comes, now what happens? Okay, this example clearly illustrates that three phase system is far better than single phase system. So now the question comes, what is about other systems like 2 phase, or maybe 4 phase, or maybe more than 5 phase, and something like this? What is about? That means why not we use 2 phase or 4 phase or 5 phase? Why not we use? So let us make a comparison to understand that why 3 phase AC supply is always used. Why 3 phase AC supply is always used? So we should make a comparison. Okay. Now for a single phase supply, this is the voltage. This is the voltage equation, Vm sin omega t. Simple. Now what will be the power output? Power output is Vi cos phi, which is discussed in the previous way. So in AC circuit, power output is Vi cos phi. Now the nature of this power is that it is always pulsating in nature. It is always pulsating in nature. So for single phase circuit, power output is always pulsating. That means with respect to time, if we plot power as a function of time, then power should be like this. it is always pulsating in nature. Sometimes it goes high, sometimes it reduces, so it's something like that. So power never constant, never is a constant term. So that is a problem. So if power is fluctuating, then from power the torque developed. From power torque developed will also be pulsating. So that is the problem. In actual problem in operation. So that is the power output. So Vi cos phi. Secondly, we require number of conductors too. That is because one is for, as already explained, one is for this. So if this is single phase, so this is conductor number 1 and the return conductor is conductor 2. Now, when the single phase AC supply is there, magnetic field produced is always static. It is a constant value magnetic field. Now let us go into the second two phase. So in case of a two phase supply, two phase voltages are, one is Vm sin omega t and another one is sin omega t minus 90 degrees. So in case of two phase supply, so two conductors are placed in this fashion. If suppose this is the conductor 1, if this is the conductor 1 dash, the second conductor should be placed like this, 90 degree to each other, 2 dash. So naturally, if the displacement is 90 degree, then the EMF induced by them is also lagging by 90 degree. So this is, so due to this fact, V1 plus V2 or maybe I1 plus I2 never 0, is never equal to 0. So due to this fact, if we use two phase system, we require three conductors. Because one conductor is for neutral current to return and two conductor is for the live. Power output, in case of a power output, it is 2 Vi cos phi, which is constant. So in case of a two phase supply, we get a constant power supply. That is an advantage, of course. And magnetic field, that is a rotating magnetic field. However, the main problem here is that we do not get I1 plus I2 is equal to 0, so we require an additional conductor for the return path for the current to go to the neutral. So that is the one problem. Here is that with the two phase. Now with the three phase, first of all, we require three conductors. For a balanced system, of course, we require three conductors. So power output is 3 Vi cos phi. And which is also constant. The EMF equations are like this. It is already explained. Magnetic fields are three phase. Three phase magnetic fields are rotating in nature. That means if you give a three phase supply, an alternating or a magnetic field is created which is always rotating. That rotating magnetic field, always rotate with a speed of synchronous speed. So it is rotating with a constant speed always. The rotating magnetic field for a three-phase supply, it is rotating at a constant speed. Due to this reason, the machineries developed for that means in the field of electrical engineering, the machineries developed with three-phase supply are always self-starting. You do not require any external mechanism to start them. They are self-starting because of this fact. They are rotating they have rotating magnetic field. Now so one question can come, so why not, if three-phase supply is can give 3 VI cos phi, then if you go for higher phases like 4 phase, 5 phase, 6 phase, so it will give you n VI cos phi. Okay, so why not we adopt that? Why not we use more than 3 phases? The answer is, you see, for more than n phases, if we solve this equation V1 plus V2 plus V3 up to Vn, it will be 0, I1 plus I2 plus I3 up to In, that is also 0. So we do not require additional conductor for the return path of the conductor. So we require n number of conductors for n phase system. Power is n VI cos phi, that is also true. Power output is also constant. Here magnetic field also rotating in nature, rotating magnetic field, just like in case of 3-phase supply. But still it is not used, because you see, if you adopt 4-phase system, 5-phase system, so the overall power system, structure of the power system, construction of the power system is too much complex. There are lots of issues regarding that. That means you require, if you use 4-phase, then you require 4-phase transformers, then you require 4-phase transmission lines. So to manufacture those items or machineries with higher phases, it is extremely difficult, costly, and it is impractical. Also impractical to achieve. So for 3-phase system we require 3 number of conductors, also we are getting 3 VI cos phi. So we go for always 3-phase system to make or to get our system as practical as possible. We do not use more than 3 phases only because of cost, because the structure and other issues, costing, the manufacturing process of the power apparatus is extremely difficult, extremely large power system, which is not possible to achieve. So due to this reason, we do not go for higher phases, we always stick 3-phase system. We always use 3-phase system as our standard. So this is the reason why 3-phase system advantageous over other systems. So let us quickly go through this point. So first point, it is mentioned lesser conductor materials will be required. So as mentioned, a lesser conductor materials is required. See, as you see, we need only 3 materials or 3 conductors to generate 3 VI cos phi, whereas in case of 2-phase system we require the same number of material to reduce 2 VI cos to generate 2 VI cos phi. So that is the one advantage. Second one is, now lesser machines will be required. So if just like this, so if we use 3 single phase supplies separately, we require 3 different machines. So let us say this is machine 1, let us say this is machine 2, and let us say supply 3 it's machine 3. So instead of having this, if we require or if we use only 3-phase supply, so we require only 1 machine. So that is another advantageous thing. More power can be transmitted, as seen here. It can transmit 3 VI cos phi. It is the highest. Voltage regulation will be better. Now what is voltage regulation? Now you see, voltage regulation is actually, it is measured to calculate the difference between Vs and Vr, that is the sending end voltage and receiving end voltage. The difference should be as low as possible. So for our system, if we use lesser number of conductor materials, then lesser voltage drop will be there. So Vs or Vr will be more closer to each other. That means Vs minus Vr. Why this is difference? This difference is basically due to voltage drop. This difference basically due to voltage drop. If we use lesser number of conductor material, then it is guaranteed that we have lesser voltage drop in our system. So if we have lesser voltage drop, then Vr should be closer to Vs. So voltage regulation will be better. Now as we require lesser number of conductor material, we have less cost. Already I mentioned 3-phase motors are self-starting because of rotating magnetic field. Now this point, domestic and industrial consumer can be given supply from the same source. That is also very important, one very important advantage. Like suppose you have nowadays it is very common in practice. Suppose you have your house. It requires single phase supply. Right? And in nearby to your house, there is a big mall, shopping mall. Big mall requires 3-phase supply. Big malls require 3-phase supply along with the neutral conductor. So this is of course RYB and N. So this 3-phase supply must be given to that mall in order to cater all the loads. However, for your house you need not any separate supply. Just you can tap one phase and neutral to take supply from that source. So what is happening here is that this house is domestic supply and this is commercial supply. They are given power from a same source. That is quite advantageous for the 3-phase system. So that is why it is mentioned domestic consumers and industrial consumers or commercial consumers, whatever, can be given power from the same source. So we have seen 3-phase, just the introduction of 3-phase system, how 3-phase system is generated. It's just like that in case of single phase system, and we have seen advantages of 3-phase system over single phase system and other phase systems. And we have seen a comparative assessment where we have understood that 3-phase system is better to use for many reasons, like costing, like more power transfer, like better voltage regulation, and so on. So with this I am ending the first part of this module 3. From the next part or from the next session, we shall discuss the different connections of three-phase supply. Thank you.